Yeah, I apologize. Oh, you don't have to listen.
Yeah.
I think I got there, but I'll listen. It's like it's on.
Well, everybody, welcome. Thanks for showing up on this pretty Friday afternoon. You got a real treat. I give you Ben Gobler who's going to tell us all about knots.
Yeah, do Mark. I'll get my side.
Oh, yeah, sure. See, you hope on this one yet?
No, yeah. Yeah, I like that. Very tricky, but not like something. Great. Just all the upside, so that's nothing, that's not discussed. Compass was good. Why you're not a bitch. My opinion. Why you're not a. Don't shut it. It's out. They don't. And there isn't. Okay. All right. Also, yeah. Thank you. Okay. Yeah. So thanks, Kim. And thanks, everyone. Yeah. So I brought for today a few questions about just untying knots in, let's say, unconventional ways. So the first question I have about knots is this: take a rope, and then let's tie a knot. Rope. Okay, I think I can stay. Okay. All right. You can make a mess. Okay, so this happens. You have some kind of knot, right? And then you want to untie it. So what you do, you look for where the ends came from. So take the loose end, right, and then you feed it through where it came from, and then okay, it gets simpler, and so then you do that again, find another spot and send it through. Okay, so that's the normal way to untie a knot. But now here's the sort of interesting question. So if you have let's do a knot again. So now instead of using the loose end, what if instead you could do all of the untying in advance in the form of another knot? So you just kind of do like this, and then you feed it along the string, right? So so they get close, and then sort of interact, and the crossings kind of do a thing, and something happens, and then maybe it can all sort of fall apart, right? Okay, so yeah, so is that possible? Can you untie a knot with another knot? That's the question. Sure. Yeah, so it's kind of a strange thing. Actually, with an audience like this, I usually like to ask for your do like a quick poll, sort of ask for your like gut instinct. I haven't really given you much time to think about it, but from your own personal experience with knots, I'm wondering if you sort of just at the beginning have a feel like you're feeling one way or the other, like you think maybe this should be possible or this is impossible. So I'm just wondering if where you're at right now. So let's just give you a show of hands. So right now you're thinking this is not possible. Not. Skeptics. Okay, a few people skeptical in the back. Okay, so that means maybe this is possible. I believe. Wow. Okay, that's great. Now maybe I guess I should give sort of the conservative option, which is maybe you don't think that this can be done for. Maybe you can't do this for every knot, but maybe there's at least one knot that can be untied. Maybe you're in that group. Okay, actually, some people raise their hands. Okay, yeah, that would be really cool, right? Well, so let me not say, or I won't give away the answer yet, but I will say that there's a nice argument for this question that's related to this false proof that 1 is equal to 0. So I want to start there. Right. Okay. So I would like to share with you a proof that 0 is equal to 1. See what you think of this. Start with 0. Okay. And then write 0 like this. So 0 plus 0 forever. Still 0. Okay. And then, well, okay, so this 0 is 1 plus minus 1. Okay, so just rewriting 0 in another form. Okay, actually, all of these zeros are 1 plus minus 1. So just writing 0 as in another form. Okay, and then Well, so, okay, now this is a big addition problem. The parentheses aren't really doing anything. I just put them in there to help see where I was going. But, we can just put the parentheses in a different place. But I'm not reordering or anything, just, changing the grouping. The addition is associative, so just, group them this way instead. And then, okay, so these are -1 plus 1, that's 0, and that's 0, and that's 0. Okay, so now it's 1 plus some zeros, and that's 1. Okay, I finished the argument. So if you were agreeing with me the whole time, then maybe you got fooled a little bit. Okay, so what exactly was wrong? I was trying to be convincing, but I definitely lied somewhere because 0 is not equal to 1. So what's the problem with this? It's pretty convincing. I think if you shared this with maybe a younger sibling, they would be totally convinced and probably questioning things. Yeah, any thoughts? What you can point to where I went wrong here? Yeah.
The second sum isn't convergent, so you should be able to say that it equals anything.
Oh, good catch. Okay, so that the calculus students will know that there's something wrong with this +1 -1 forever, adding forever. And yeah, you're right on it. So that's a mistake. Actually, all of these are mistakes. And really, it's the problem is with this adding infinite numbers together. So again, our calculus students will know that adding infinite numbers together can be dangerous. In the sense that you might not always get a number as the result. And this is one of those cases. And if you do this alternating +1 -1 infinite sum, it doesn't converge. So this is not a number. So actually, it doesn't really make sense to say that it's equal to anything. It's not a number. It's not equal to anything.
So people don't say much about this, but that's always bothered me too, because you apply associativity an infinite number of times. Right, to make that switch.
Yeah, so isn't that kind of frustrating? It's like, somehow it's okay to just replace 0 with +1 -1, but it isn't okay to do that as many times. There's definitely a problem with the infinity. We're taking advantage of the infinity to make this false argument. Okay, so it's not true. So 0 is not equal to 1. There is a mistake. But it turns out that this kind of argument, this style of reasoning, works in other mathematical settings where infinite addition is not problematic, or it doesn't have the same kind of convergence problem that numbers do. It turns out that knots are one of those settings. So the plan is to make an argument using this similar style. I think we'll spot what I'm doing. So let's go there next. Okay, so for knots, let's start with the empty rope. Okay. And then tie onto the rope a knot, call it K for knot. Okay, let's suppose that this knot K has another knot L that unties so let's assume that that L unties K. You tie them next to each other, they untie, and you get back the empty rope. And by the way, I'm just drawing these little graphics. I'm not sure. Maybe these two don't actually do that in real life, but just for the sake of the right. Okay, so we're making this one assumption. Suppose that this K and L undo each other, and I'm just using a notation. I'm using the hash to mean tie the knots on the same string next to each other, and then writing 0 to represent the empty rope. So this will just be a short way of writing when you tie K and L next to each other, they untie each other, they cancel out. Okay, so before we make the infinity type argument, there's one thing we have to think through first, which is what happens if you tie K and L in the reverse order? So L supposedly unties K when it's on the one side, but whatever kind of interaction that happens, the crossings kind of interact and untie. What happens if you put L on the other side? I mean, does it also untie on the other side? I mean, it's different sides of the string, it's different sides of the knot, so I guess it's fair to think that maybe the interaction should be different on the other side. But it turns out actually that L does untie K, and here's the really nice argument for it. So all you have to do is take the knot K and pull it open really wide, and then take L and pull it small. So just change the just pull the part. Okay, and then you take this knot here and just feed the string along. Like, you know, you can sort of move a knot along the string by feeding it some slack and then running it through on the other side. So we can remove this knot along the string. So we start sending it along, and then and keep going so around and through, kind of like a tram or something, like a tram bar on a line that goes all the way around and comes out on the other side. Okay, and then you can just fix the sizing again. So just pick up the normal size. Okay, so I'm making a visual argument that actually you can change the order of the knots are tied on the string. Using this process, you can just make one small and send it around. Okay, and of course they cancel. We're assuming they cancel on in this order. Yeah, so that was K goes out. Right. Okay, so we were assuming that K and L cancel. What we're learning is that L and K also cancel when they're tied in the other order, because if you want to make them cancel out, you can first change thread 1 through, change the order, and then make them untie each other. Okay, so we're going to do this, and now it's time to make this special argument. Okay, are you ready? So what you need to do is tie this. So that's K, and then L, and then K, and L, K. You do this alternating, tying them to infinity. Tie them alternating forever. Okay, so what is this knot? What is this? Well, if you ignore this K for the moment, there's an L and a K, and L and K are when they're tied next to each other will cancel out. They can become the empty row. And so again, this L and K and that one and next, they all pair them off and they all vanish. They all cancel each other. So actually, this whole thing is just K in disguise. It's just a fancy version. Okay, we'll go back because we can also shift the brackets, shift the pairs, and here's a K tied next to an L, and K tied next to L will cancel, and so will this K and L and so on. And so yeah, all of these pairs cancel out, you just get the empty row. So that whole long sequence is also the empty row. Okay. So just show it that this mega knot is both this and that. So they're the same thing. There's a 1 equals 0. Okay, K equals 0. So what we just learned is that the knot K actually has to be the nothing, the 0 knot. That's okay. So in words, the only assumption we started with was that K could be untied by another knot, and we just proved that K then has to be the 0 knot, which I guess let's have that be the name for the empty row.
Why is this argument okay in this set, not in ones and zeros?
Yeah, thanks for asking. So okay, you're right. I did just lie through a proof, and now I'm giving you another proof. So I know your senses are heightened. Like, why is this okay? But it's not okay for numbers. Yeah, let me mention that in just a moment. I just want to say one other thing about this, which is this is just a direct argument. If you believe it so far, maybe I still need to do some more justification. But the contrapositive statement, or another way to phrase it, is that non-trivial knots don't have knots. Okay, yeah. So why is this okay for knots? But it's when it isn't okay for numbers. Yeah, so okay, actually, maybe I didn't put it aside. So maybe I just want to say some words. So the question is, why is this okay? Well, it's okay if this is a knot. So what is a knot? So yeah, I guess we have to back up and ask what counts as a knot, and the way that knots are defined in the theory is just pretty much this: just any arrangement of a rope in space, so that the rope isn't like intersecting itself, or we call it embedding. So any embedding of the rope in space counts as a knot. So this, like, the rope is in space, that's a knot, and that's the definition. So there's no there are no other restrictions. There's nothing to say about how complex they can be. Nothing to limit the sort of infinite intricacy or complexity. Now for this, for knots, you see I'm making the knots smaller as you go along the string, and that's for a reason. I guess maybe there would be nothing wrong with just tying all the same size and just tying forever, but maybe it's better if the whole thing is compact, like it's fit it on the screen. I'm not sure actually if that's important. That it has to be in a closed space instead of going on forever. But for knots, we can actually take advantage of the fact that we can make them smaller. So mathematical knots, the rope isn't like this. Mathematical knots rope has no thickness, has zero thickness, it's just an arc in space. So we don't have to be concerned about, like, oh, maybe you can't tie them small because the rope will be too okay, but actually this is supposed to be like infinitely thin rope, and so of course I can't draw it if it's infinite, so I have to give it some thickness presentation, but you just have to imagine that actually it's kind of infinitely thin arc through space, and so we can make the knots as small as possible, and I can space them like I draw them at, like, this is the interval from 0 to 1. I can draw 1 and then 1/2, a quarter, and an eighth, 16th. And each one I can draw from half the size, a quarter of the size, and so you can fit all of these on a string, and that's just fine. There's some infinite string out there in the mathematical universe that has this kind of infinite knots. If you ask me about some point on it, I can tell you what it looks like there, and that's perfectly good. I think I maybe have given more details than, or maybe it's still not convincing. We can talk after the lesson. I guess there is it's important. I agree that it's important that we explain why this is okay. But the answer is that actually yes, this thing is the short answer is yes, this is a knot, and so the argument is valid, and it really is true that the only knot that can be untied is the sort of yeah. I think that's what so okay, I guess the answer is kind of yes and no. If maybe before you had said that you thought that it's impossible, you're right. But also, if you said that it is possible, you're also right, because in some technicality, the empty rope is also kind of knot, okay? Also a rope in space. So that there is a knot that could be undone, but it's kind of a disappointing answer. It's the nothing knot. But this has an interesting consequence. I guess I was going to say, yeah, that's right. This argument is called the Mazur swindle. Our arguments in this style of doing the alternating something as inverse forever and then canceling in pairs. So it's the same after Barry Mazur. There's a really nice documentary about he's a professor emeritus at Harvard. So if you're curious about and then maybe more about this. See, there's a nice documentary on YouTube. Yeah, okay, so one consequence of this Mazur swindle is that it has to do with this the fact that you can't cancel knots. So let me tell you about this. Okay, you might have thought before we started that you could take the empty rope and that you could sort of, without engaging the ends of the rope, you can kind of do something to produce like a pair of knots. Like I'm picturing this. Like you could start with empty rope and then you can sort of do something to produce a pair of knots on the string next to each other. And what we're learning now is that actually that's impossible, because if it was possible, then you could just do the whole thing in reverse and you would be canceling a pair of knots, which gets done. So so the empty rope actually you can't sort of magically produce a pair of knots next to each other, which maybe sounds disappointing. It's actually really important. It has to support consequence in the theory of knots. So yeah, so what I'm picturing is like you have this big messing up, like maybe this is your headphones. This never happened. Something is and so maybe you're not really sure how to start, so you just kind of start pulling at it, and then maybe at some point kind of like whoa, and then it comes apart into like a bunch of smaller knots. Like this has ever happened, like you're just sort of going at this big knot, and then it sort of unfolds and you get like separate knot pieces. So this is a property of knots. Say that a knot that decomposes like this into, let's say, two or more non-trivial knots, we call this thing composite. I mean, it kind of factors, like numbers, that factors in small knots. But they don't all do this. So knots which can't be sort of teased apart into separate smaller pieces, we call prime. So there are prime knots. So another way to say on previous slide was that the empty rope, the zero knot, is prime. It can't be written as the it's like two or more knots connected. Okay, and so okay, so where do I go? Well, if you have a knot and it might be prime, so then you just stop it. If it's composite, you can pull it apart into pieces, and those pieces could be prime, but maybe the pieces are also composite, and you can sort of pull them apart too, and their pieces, and so on. And eventually, if you pull it apart enough, you'll be left with just a string of prime knots. You just keep pulling them apart until you can't anymore. And so that's the kind of like prime decomposition. And there's this amazing result that every knot has a unique decomposition into prime knots. And that's okay, so maybe that's surprising because I thought that it sort of depends on how you pull it apart. Like maybe it pulls apart in multiple ways, and depending on how you pull apart the part of the knot, you might get certain primes in the very end or others. And it turns out actually that no, they're unique. There's a unique way to do it. It's always with the same prime. That's really cool. It's like prime factorization for whole numbers. Also, there's a kind of analogous prime factorization theorem for knots. There are primes and everything else is the sum of like it's just a bunch of primes together in a string. I don't know. I was surprised when I heard about that. Okay, but so the reason I'm going here is because if the empty rope could be factored into a pair of non-trivial knots, then this couldn't happen because you could just take the rope and produce a magical pair of knots, and it wouldn't be unique. So the uniqueness relies on what we proved with the Mazur swindle, which is that empty rope you can't just produce knots. However, you can't just produce pairs, canceling pairs wherever you want. So that, yeah, so that's actually necessary for this. Okay, so so you can't cancel knots, but we could maybe hope for the next best thing, which is maybe you can at least simplify a knot with another knot. Okay, so you have a knot on the rope, and then you're going to tie something next to it, and then you hope that when you push them together, okay, they won't cancel out, but maybe you could at least get the thing simpler. Like maybe it was the headphones knot, and you're just hoping that you could tie a new knot and send it in, and it will just kind of make it look better. Okay, so that's not out of the question. Maybe that's possible. Well, okay. Yeah, but hold on. So what do we mean by simplify? Well, how can you judge how simple is a? We need a metric or some way to measure the complexity of a knot. And there are a few classical ways to do that. Let's talk about two of them. So the first way that you can measure the complexity of a knot is you can look at the diagram and you can count how many times the rope is crossing itself. So these are called crossings, and crossings are part of the diagram. I guess I want to just make a subtle point here, which is that the actual knot in space doesn't cross itself ever. No, it's just a loop. It's just the netting of the arc in space. It doesn't actually cross itself. It's just when you kind of pick a view on it, you like flatten it and draw it on the screen, that there are places where your drawing has to cross itself. Okay, the crossings aren't here. The crossings are in the drawing. And so then actually it depends on how you do your drawing. Like here are two other drawings of the overhand knot. And like here's one where you just give the rope a small like little loopy, like a small twist. And that one is it doesn't look at all like that. So maybe I can reproduce it. I think if you take this and then okay, so this looks like the original, and then this, yeah, it's like see now it looks like that. Maybe it's supposed to be this way. Yeah, so okay, so you can have different drawings of the same knot. These are the same knot, it's just a different diagram. Sort of viewing it way. And these ones have these are four crossing drawings. And it's easy to add more crossings. You can just like form you can do like that, you can just make some more twists, right? That creates more crossings. Or you can take part of the rope, you take like a bite of rope and just overlay it, right? Let it pass behind another rope and just get more crossings, right? Or you can like wiggle the rope in front of another and just get lots of crossings. It's easy to make more crossings. But what we really want to know then is what's the simplest diagram you can make? Or like and by simple, so what I mean is the fewest number of crossings. So for a knot, we define this crossing number to be the least number of crossings among all possible diagrams of the knot. So you try to think about all the different ways you can draw this knot, and then pick the one which has the fewest number of crossings, and then that number of crossings will be the crossing number. So this overhand knot has crossing number 3, which I'm trying not to use so much notation in this talk, but we'll just use this lowercase cr for the crossing number. The crossing number is 3, so it turns out to show that you really can't draw this thing with fewer than 3 crossings. You can't do it with 2, can't do it with 1 or 0. Yeah, so the overhead knot at its best can be drawn with only 3 crossings, and so that's the crossing number. And don't you agree that in some way that measures a kind of simplicity or complexity of the knot? Like if the best you could do was draw a knot with 10 crossings and complicated, you couldn't get it to look any simpler than 10. I don't know. So, okay, so we have, at least we've decided on a way to measure the complexity. So then the question is, if you have a knot, I chose the more complicated explanation. You have a knot, and you tie something next to it so that when you push them together, the crossing number goes down. And you simplify it, and you lower the crossing number by bringing in another knot. Maybe you can't get it all the way to 0, that would be untying. But maybe you could at least get a little bit, like a little lower. Okay, so not out of the question. Well, okay, yeah. So how could we find the crossing number of this new thing? Well, okay. Well, if you draw the optimal diagram for the first knot, then count the crossing. That should be the crossing number of the first one, and then draw the other one optimally well, so that it also has the least number. That's its crossing number. Well, here we're looking at a diagram of the sum, and it has, well, okay, there's 7 crossings, which is the sum of their crossing numbers. Okay, so that's like a benchmark, right? You can at least do that well. If we put that in words, say that the crossing number of this sum of the two knots is at most the sum of the crossing number. So we just found a diagram that has this many crossings. The question is, can we do better? I mean, when you combine them, like when you put them together and you rearrange the diagram to have even fewer than in this case 7 crossings. Well, actually, we were hoping to do better than 4. The goal was to simplify the original knot. We were hoping that this thing could actually be even smaller, like even less than just a problem. Okay. And yeah, the difficulty is that when you bring in a new knot to hopefully do some damage, we're adding more complexity, we're adding crossing. So maybe now, so I think it might be too much to hope for that we could actually get this whole thing to be lower than just the crossing number K. So maybe we adjust our host and say, could this ever be less than the sum? Like, can you ever do better than this picture? And they combine and you could get it down to maybe 6. And that's an open problem. But it's been conjectured that actually there's equality, meaning this is the best you can do. When you tie 2 knots together, the crossing number of this thing we think is probably just that. You actually can't simplify them. You can't do better. But it's an open problem. So it's known, the equality is known for some common families of knots. But we haven't yet seen a counterexample. So no one has found 2 knots where you can find a diagram which has fewer crossings than just some of them. Okay, that's too bad. That's also a little disappointing. We were hoping to simplify K, and it turns out to actually can't even simplify the K and L together. So really too bad. But it's interesting, and I think I also wanted to show where it takes us. Yeah, so the crossing number. You might be wondering, like, why don't we know this? Like, shouldn't we be able to just test all these pairs? We should be able to just put knots together with computers and see that the diagrams can or cannot be reproduced, right? And so maybe you're wondering, like, why haven't we answered this already? Turns out that doing this is kind of challenging. And here's an example of that. So here's a knot that has, I counted earlier, I think it has 10 crossings. Check. 1, 2, 3, 4, 5, 6, 7. Yeah, okay, so 10 crossings, but this might just be kind of an uglier presentation. You think that maybe the crossing number could be reduced. For 10, maybe it's a little bit less. I don't know. This one's tricky because, like, I don't know. You can imagine kind of wiggling the strand. These ones are really up together, and this like hook is going around the web, so that's not good. So that's a loop around the itself. Okay, so it's presented in kind of a different way, but you can sort of fiddle with this. I didn't tie this one, but actually it so left to right actually unties all the way. This is actually the loop. That's something I want to say too. So I've been presenting the knots like this on the string with the loose ends. And the whole time I'm just keeping the ends kind of out of the way. I figured this is kind of a nicer way to look at the knots, like you sort of are familiar with how knots look like this. But for mathematicians, we sort of get fussed about having loose ends because the knot could accidentally slip off the end and come untied. So what's more conventional for presenting knots is just to take the ends and glue them together to sort of trap the knot on the string. But hopefully you agree that it kind of still looks the same. Like you can present it as here's the knot on a string, and then the ends are just kind of put together. So this is supposed to be like that. It's just on a it's just the ends are glued together. And then the thing is, once you glue the ends together, you can start to change the way it looks. Like, actually make the overhand knot look like this kind of three-way thing, or give it another shape where now it doesn't really look like a knot on a string. You can't really see where the ends used to be. So that's kind of like this one. If you're thinking this kind of looks like a wad and not what I showed before, it sort of is. You just have to first put the ends together. But really, it really is just a knot on a string. And then the same way, the empty rope, when you put the ends together, is just a loop. So this loop represents the nothing knot, just with the ends together. I just wanted to clarify that. But yeah, it turns out this thing was it reduces all the way. Maybe you were anticipating that. I chose this one special. But yeah, the idea is that it actually can be really hard to tell if you've had the diagram simplified all the way. These diagrams can get messy, and this is just 10, but knots could have 10 million crossings, and then or the diagram can have 10 million crossings, and how do you know that it's actually doesn't just reduce back down to a loop? Just the zero time. So yeah, just hopefully I can convince you a little bit, persuade you that finding the crossing number is difficult in general. But it has been done for small numbers. So here's the classic table of knots. So these are representative of some of these the ways you can tie something on the string and then move the ends together. So that 3-1 was overhand knot, but with the ends glued together. So the way these are labeled, so each of these knots are given conventional names, and the number is the number of crossing, and the subscript is just they've been put in, or I guess a random order kind of they're numbered. So there's the knot with 3 crossings. The overhand knot is, in this sense, the simplest knot that isn't just nothing. And then you get 4 crossings, and then 5. So these are all the way these are drawn. This is the best. These diagrams are the best you can do in terms of getting the crossing number. These are all those optimal diagrams, and I just think it's really amazing. So this goes just up to 8 crossings. Yeah, it's missing a few things. These are actually just these are just the prime knots. And now I think we can argue for why I can give an argument for why it's not useful to include composite knots, because the composite knots you make by taking 2 or more prime knots and putting them next to each other. And if this conjecture really is true, then there's no other way to arrange that diagram with fewer crossings than just drawing them next to each other. So the composite knots that would go in this table would just be some of these put together. If the conjecture is true, it won't actually reduce any further. So there's no need to draw them, because you can imagine them. They're just sequences of these. Yeah, Jim, and you're right too. So also some of these knots are distinct from their mirror images. So there are other prime knots than these, but they'll look just the same, but in a mirror. So those also are included, just to keep the data. I'm really amazed that this is possible. I mean, what this is saying is that like this thing and that thing are like, you can't turn one into the other, or that they're all distinct. Which I don't think that's clear just looking at them. I mean, even if you played around with it for a while, you might not be sure if you've Like, you've actually tried all the ways. So what's amazing to me about this table is that it's there are no duplicates, but also it's exhaustive. There are no other knots with 7 crossings, prime knots with 7 crossings that isn't listed here. So if you ever make something with 7 crossings that you can't do better, it's going to be one of these. You just have to shuffle it around. Amazing. Like mathematicians were able to work out like this is one of each. no repeats, nothing missing. And that was effort that I guess took a while. And there were in the history of knot theory and people tabulating knots, there were some mistakes, but and now we have more tools to tell when 2 of these things are the same or different. You don't have to do by inspection. There in knot theory there are other tools that you use to figure out if these things are different from each other. But I also wanted to show you this picture. So this is from Tate, who was one of the pioneers in tabulating knots. And here are some of the sketches of knots with 10 crossing. I mean, it's so beautiful. It's like a work of art, but it's also math. So these are all 10 crossing knots, and I suspect that they're all supposed to be distinct. And I mean, can you imagine coming up with like tabulating knots like this and being sure that you haven't like accidentally counted the same one twice or that you haven't missed anything? It blows my mind. I'm just really amazed by this kind of thing. But I was checking before the talk, and I'm pretty sure that we have now an exact number. So we've done the tabulations for all knots with up to oh gosh, I'm gonna get it wrong. I was gonna say 20. Actually, maybe check me out. It might be that it's actually 10. Yeah, so I should have brought the room so I could say. But we are certain about the number of prime knots up to some number of crossings, something between 10 and 20, and maybe I'm just confusing the stats. But so maybe you say like, well, actually, that's pretty low. I mean, only 20. That's a 2-digit number. Knots can have millions of crossings, and they only can be 20. But no, it's just difficult. It's a difficult problem to work out.
So is there, if you go to the previous slide, is there a pattern in terms of how many knots you have for say 7 crossings? So here you show 1, 2, 3, 4, 5, 6, 7. For the 8 one, 1, 2, 3, 4, 5, 6, 7, 8, 9. So is there a pattern to the number of unique knots you have for each crossing number?
Okay, yes, the question is about how many of these things there should be in the table. So I think that the sequence is known for the first. I was going to say the 10 to 20 terms. I think it's exponential. The number grows exponentially, but I don't think there's a closed form for the number.
I'm sorry?
I don't think that there's a closed form expression for the number for any minute. Good. Yeah, but it should be that we should expect there to be lots more with when you offer more crossings, you'll have more creativity, more potential, and I believe that is like they're exponentially many.
Is there reasoning behind the subscript? Like in the next picture, it looked like it's like sectioned off. There are like the little vertical lines that I assume means whoever was making it had some relationship between those and some reason for grouping them. Is there a similar like are all of the 5-1, 6-1, 7-1, are they like in a family somehow?
Yeah, that's a neat observation. I noticed those grouping lines, and I haven't looked into the notation that that Tate was using here for these. I did just want to show off a picture of what a tabulation of knots looks like, but I'm not sure. Okay, yeah. We'd have to read up a little more. Yeah, so that's the story for crossing number. Sadly, you can't reduce the crossing number by tying another knot. You actually you not only you can't reduce it, but you can't even do better than just putting the 2 knots next to each other. So not great. But there are other ways to measure the simplicity of the knot. So, yeah, so here's another method. We take the knob, and then, you can do, what we call a crossing change. So at one of the crossings, at one of the places where the ropes cross each other, you can, so watch here, I'm gonna make a change there in the picture. You can change which rope is on top. I just switched the one that was behind and brought it in front. You can change the order of the ropes, like you let them pass through each other at the pole. Okay, and can you see what that does to this now? Now there's just this loop that's just resting on top. We could just that back, and now it kind of fell apart. Okay. So after making that crossing change, we've fundamentally changed this knot. It is now the same as just the empty rope. Okay, so we say the unknotting number is the least number of crossing changes that need to be made to untie the knot. But for this, for the overhead knot, the unknotting number is 1. You just change one crossing and it's untied. So that's different because the crossing number is 3. The unknotting number is just 1. And in general, you probably shouldn't have to change all the crossing. Like the crossing number is 3, but the unknotting number, you probably shouldn't have to do cross changes everywhere. I think if you did that, you'd probably still be not. Yeah, it's the unknotting numbers are usually smaller. You just have to make a couple changes and then the whole thing unravels. Yeah, do you believe that the unknotting number should exist? Like change enough crossings, it should always come undone? I was thinking about maybe how to argue that. And I thought of a couple of things. One is you could just pretend that the rope for a moment is sort of like ghost rope and it can pass through itself. In that case, you could just the thing, right? You could just shake it and the knot would come out. And then you go back and watch the footage and see every time the rope passed through itself. That's a crossing change. So there should be some number of crossing changes they can get what they undone. There's also an algorithmic way to do this, which is start at one end and it's like a greedy algorithm, it's like a brute force. You just start tracing the knot, and every time you reach a crossing, you just force, if it's your first time there, you just force that to be the over string. And then later on, when you come back to it, you've already been there, you go under. Let's see this. A little impromptu. Okay, let's draw. Let's draw. So okay, I'm gonna make it more interesting. Okay. I made a knot. Okay, so I think it looks like I've done a double over. So maybe this thing actually is just it's just 0. But no, I shouldn't have done that. So let's see. Oh, anyway, okay. Just let's imagine this thing is actually knotted. So what you can do is you pick a starting point, and then you start going around. And every time you reach a crossing and you haven't been there before, you force that to be the over string. And then so here, if we reach this for the first time, so we're going to force that to be. We're going to make a crossing change. Make a crossing change. And then oh yeah, I'll make a crossing change here as well. So okay, this one continue, and another crossing change there as well. And then we've been here before, so we have to go under. And then we've been here before, so under. I haven't been here, so and then I've been here under, and then under. So we did make a few crossing changes, but what happened now is by forcing ourselves to go over, we sort of this rope is just in a pile. Like we just traced it from front to back. So this thing is now just resting on top of itself because we always started on top, and always every time we got back around, we went behind where we were before. So so this is completely on top of it. Maybe I could have used a different color. This is hard to look at, but that's the idea. Okay, so you can, by making some crossing changes. Right. Okay. So so let's ask the same question. You have a line. Can you with something across the number, and you tie something next to it so that together they have once you combine it, this thing can be untied with fewer crossing changes than its target. That's the question. Well, oh, hey, spoiler, right? So let's see for that. I want to look at the picture first. So with the knots just next to each other, you can untie. You can untie this one with its uncrossing number of crossing changes, and then separately you can untie this one with its uncrossing number of crossing changes. So if you do them separately, you can untie them separately without ever combining them, and it will be untied with the sum of their crossing numbers, crossing changes. So that gives us a start. The uncrossing number of the thing together is at both the sum of the individual crossing numbers. But really what we were hoping for, again, remember, we're hoping that once you combine them, you could get the uncrossing number to be even lower than what we started with. That was the idea of simplifying. Now, and our starting place is the sum. So it's kind of the same issue as the other simplifying the crossing numbers, is that by adding more knots, we're also adding more potential crossing changes. Okay, so maybe it's too much to hope for that this amalgam thing is going to have fewer than just one of those crossing changes needed. So maybe we again be more realistic and change our hopes that maybe together they could require fewer crossing changes than the sum than when they're combined. Well, fortunately, it was conjectured that there's always the equality. That you actually can't do any better than just sum, which is too bad. But I say it was because this was actually disproven. It was less than 3 weeks ago. A paper came out on the arXiv showing that a counterexample that actually you can do a little bit better than the sum. So I want to finish by showing you this this miracle example. So the authors of the paper found this 7 crossing knot, which is known to have an uncrossing number of 3. In the paper, I think they say that any 3 crossings to change will untie this. They weren't more specific, so it should be as easy as just 3 of these change the crossings, and it should just apart. But maybe double check that. And it's also known that only 2 crossing changes will not be enough. I guess if you just play around with this for some time, you'll be convinced that actually it's not it's complicated enough that 2 crossing changes is enough to reduce. So the uncrossing number is 3. For its counterpart, they're choosing the mirror image, the same but in a mirror. And so, okay, of course, it also has the same uncrossing number. That's no surprise. 3 and 3. So when you put it together, the question is, what is the uncrossing number of this thing? Is it better than 3 plus 3? So can you do it with fewer than 6 crossing changes? And the answer is yes. Do it in 5. If not a way to do it is 5. And would you like to see how that's done? So, okay, the first thing you have to do is take the ends and you have to hit it. So we do the same thing as the author did. We'll make this into a loop, and then you have to do a little refactoring. Okay, so you just kind of rearrange it, and if you spend some time, you get it to look like that. And then, so this is from that paper. So the authors were they're saying like we should take this red thing and move it somewhere. Take that red thing, so rearrange, get these things, and you sort of lift and twist. So you create some more crossings, and then do crossing changes. Right. Okay. Yeah. See, that's the actually what I say. Right. Okay. So two crossing changes have happened. Let's keep going. So they point this way. A little bit of a maze. So we made the changes, and then you take this piece and you move it, and then do some more kind of squiggling and wiggling, and then okay, there's a little more. So you go here, and then and then take this piece, give it a twist, it makes a crossing, and crossing change number 3. Okay, it keeps going. So then there's a little bit of this, okay? So a little more, keep going, you get there, it's not done yet, there's a little bit more. So you get here. And then there's crossing change number 4 and 5 happen at the same time. Okay, so that's 5 crossing changes, and you have this. Okay, so supposedly 5 was enough. So we're here now. Does that look like it's all untangled to you? It's not looking good. But it's a little more they have, so just take that and wiggle, and actually that was just a unknown. So another tricky one where it looks messy, but it's actually this. It's just okay, so it works. It's just amazing. And you're probably wondering, how did they this? So the authors explained that they had their computers running for over a decade, and just like gaining information about uncrossing numbers. They're doing it in a systematic way where they start with small knots and just try all these different crossing changes and arrangings, and if you eventually get to 0, you just see how many crossing changes you've done and say, okay, that's a good start. You know, can we do better? And then if you're ever doing a larger knot later and it eventually gets to that thing, you know how to finish, right? So they're just creating these sequences of unknotting sequences. And after 10 or more years of this, they set it on these sums, and one day it said, we did it. and they have this. Now, okay, I may have actually I wrote before the unknotting number was 5. I should have said less than or equal to 5, because this might not be best. Maybe you can do even better. But maybe you can actually beat 3. Maybe this can be done in 2. That would be really cool. But anyway, it's better than the sum of its parts. So that's exciting. So the conjecture. Yeah, I didn't say before like why this is difficult. I mean, for an example so simple, like it's just the 7 crossings. Again, it feels like, shouldn't we have figured this out by now? And maybe seeing the complexity of this, seeing that actually this is difficult thing to do. And the reason it's difficult, so I didn't realize this at first. When I was thinking of like unknotting by making crossing changes, I was thinking you sort of fix the diagram, and of those 7 or so spots, you just choose which ones to change. But for unknotting and unknotting numbers, it's more than that, because you're allowed to rearrange the dot in between your crossing changes. So like here are 2 arcs that aren't touching in this view, but maybe what you want to do is actually bring them close to each other and then do a crossing change. So actually, what's allowed to do this unknotting process is you can rearrange and reshuffle and shimmy the ropes. That's what was happening here. There was a lot of sort of weird movement and things happening and making things overlap so that you could do a crossing change. Yeah, so I mean, can you imagine like how you exhaustively do this? I mean, there are just so many ways to rearrange the rope and decide to make things uncross and cross. I mean, yeah, it's just crazy. So it's actually really amazing that they were able to find this and a needle in a haystack example. The computer actually found a path of things that you can try to match up and uncross and untangle the 5. Just amazing. But it does also speak to the difficulty of unknotting numbers, and so yeah, maybe you're getting a sense for why these things are not as well. They aren't as well understood as maybe they seem simple on surface, but then actually, yeah. So this is exciting. This is brand new research. It's kind of shaking up the knot theory community. People are getting excited again about knot statistics, like the unknotting number. And I was going to point to a few things to talk. There was this nice article from Content about the paper. If you like to read about these things, they give a nice. They have these nice bits from explaining the process between the authors and yeah. So if you like these kinds of articles, the process is really nice one. So you can learn more about what their process is like. And then also, And a few people this week were very kind and sent me. So Matt Parker put out a video this week where he actually, or last week where he actually follows the instructions and unties the thing, which is awesome. So if you didn't believe the pictures, you did. Watch a bunch of this. So Matt is great, and I was thinking about this too. So I grew up watching kind of like math expedition. I realized that not everyone in the department, not all mathematicians, even really know or didn't know that there are these kinds of like math communication exposition sources online. So if that's you and you've never seen Parker or Grant Sanderson, Blood Brown or Number File, go check these things out. They're really engaging. Learn some fun recreational math, things that are happening in the math world that are sort of also approachable and interesting. Yeah, so things out. And then the last thing I was going to talk was if you want to learn a little bit more about knot theory, so this we found this to be entertaining, and maybe you want to learn more about the actual theory, like what you want to see it a little bit more formal, learn more about knot theory. There's this this is like the book, the knot book by Adams. I brought it with me, so if you want to take a look, you're welcome to. I also printed out the paper if you wanted to see what it actually looks like. They're writing after the talk, so I brought both of those. If you want to check it out, I encourage you. The knot book is amazing. It's the exposition is just really top level. It's approachable and easy to read if it's your first time in knot theory, especially the first two chapters. And you'll be amazed to see like how early on there are these like unsolved questions and open problems. When I think of unsolved problems, I think like oh, that's something that people at the furthest edge of their field can do. I'll never understand. And here on page 4 or 5, you're already ready to read about these unsolved problems. So I guess it speaks to kind of the maybe knot theory is still kind of a young subject. We don't know a whole lot, but also that it's kind of approachable thing if you're looking for something to get into a new hobby. So yeah, okay, that's all. Thank you.
Any questions?
I don't know if you've looked at like other knot theory papers, but I imagine this one was like, there's this big conjecture, here's a counterexample, and then they just work for the counterexample. What else would be in this paper?
Oh, so I got to look through the paper. I think they have other questions they ask, other problems related. Yeah, we can look at it together. So yeah, it's a little deeper. It's more than just the one example, but that's
Generally, you make a new conjecture so somebody else can pull off for 0. So. Yes.
So that 7-1 knot was pretty easy to generalize for any odd number. Was there anything in the paper about how like this generalizes not just for 7-1 and its reverse, but 9-1 and its reflection, or something like that? Is there a family of examples?
Oh,
I saw the paper too. I just forgot to.
Yeah.
Weeks ago, I didn't.
Okay. Yeah. I really don't. I don't want to claim things that aren't true, but I think if I remember correctly, there is a whole family of counts.
Yeah.
Yeah. I think you're right.
Other questions?
I also wanted to respond to the question asked before about whether the infinity tying knots thing is valid. And we can talk more about that, but also I remember that I want to say John Conway also gives another proof that you can't cancel knots. He does it without the infinitude. You don't need to tie infinitely many knots. So there's another argument that avoids the whole thing. If you're curious about that. Yeah.
Others? All right, let's thank Ben again. Y'all have a good weekend and see you for another next week. Absolutely.
Okay. Where are you next week?
Columbia. Yeah. The big COLUMBIA, they don't. You have Dude, I saw that on LinkedIn. You guys all look like, I like that, but you guys should have known about this. You guys should have read every single post that I like on